We've talked about the importance of collisions between gas particles, right? We talked about how it inhibits mass transport. And so it's helpful for us to study collisions in a little bit more detail here at the end of chapter 5. Let's talk about what collision rate is. So just like how with a fusion rate, right, that would be calculated by taking the amount of gas that diffused and dividing by time, the collision rate is similarly found. The collision rate would be found by taking the number of collisions divided by time, right? We take the thing that we're interested in and we divide it by the change in time to find what a rate is. Now let's think about some things that collision rate might depend on. As you might imagine, the number of particles that you would have per unit volume, or that is to say the concentration, should play a role on what the collision rate is. The more molecules you have in a given space, the greater the chances that they're going to bump into one another, and the higher the collision rate will be. Average speed is going to play a role as well, because as you might imagine, the faster the molecules travel, the faster it's going to be for them to bump into one another. Additionally, the size of the particles plays a role, because the bigger the molecule is, the more likely it is to bump into other things. So all of these play a factor in determining what the collision rate is. And all of this is shown in the equation for collision rate that's shown here. So Z represents the collision rate, and that's equal to capital N, which refers to the number of gas particles, divided by volume, right? So that's our concentration of the gas, times 4 times D squared, where D represents the diameter of the molecule. Right? So the bigger the diameter, the more likely it is to bump into other molecules. So we see how that plays a role in collision rate. Times the square root of pi RT over the molar mass. And this part of the equation looks very similar to our speed distributions. And so we can see that molecular speed plays a role in the collision rate as well. Now, I'm not going to make you do calculations with this equation because it's kind of a bit much. But I am going to expect you to be able to recognize proportionalities in this equation. So to answer conceptual problems like the one that we're going to see in this problem here. We have 2 samples of nitrogen gas. One is at 1 atmosphere, 1 liter and 25 C, and the other is at 0.01 atmosphere, 1 liter and 25 degrees C. And I want you to determine in which sample you will have the highest collision rate. Is it in sample A, sample B, or is the collision rate the same in the 2 containers? Take a moment to think about this, and then go ahead and put in your answer. All right, having given you some time to think it over, let's talk about the answer. It's helpful to take a look at our equation for the collision rate and very carefully study the variables that we're dealing with here to see what's the same between the 2 samples and can be canceled out versus what is different between the 2 samples. In these 2 samples, the volume is the same, and so that can be canceled out. We don't really care what that is. And in both cases, we're dealing with nitrogen gas. It's the same gas. And so that means that the diameter is going to be the same. So that can be canceled out, and we don't have to worry about that. Additionally, again, because it is the same gas, the molar mass is the same. So we don't have to worry about the effect of molar mass. And the temperature is the same. Everything is at 25 degrees C. And so we don't have to worry about that. Pi and R are constants. 4 is a constant, right? So who really cares about that? And you might be led to believe at this point, well, everything is the same, so maybe the 2 containers have the same collision rate. But there is still one more variable that hasn't been canceled out here, and that is the number of gas particles, because that is different here. And to see how they're different and to see how you can evaluate which sample is going to have the higher collision rate, it's important to use the ideal gas law to relate the number of moles of gas or the number of particles of gas to other quantities that the problem gives you, like pressure, volume, and temperature. All right, from PV equals nRT, what we see is that the number of moles is equal to PV over RT. Now, between these samples, we recognize that the volume is the same, the temperature is the same, and so since the pressures differ, the number of moles has to differ, right? So that's how we're able to see that there is going to be a difference in the value of N. Because if V and T are the same, but the pressure is different, then that means that the number of moles has to be different. Now, if you were to increase the pressure, then you would increase the number of moles of gas. And as you increase the number of gas particles, right? So as we increase the value of n, then that's going to increase the collision rate, right? Because there is this direct proportionality here. If you increase the numerator, that's going to increase the value of z. And so you're going to have a higher collision rate in sample A, because in sample A you have a higher pressure, meaning that there are going to be more gas particles per unit volume, and as a result, there will be more collisions between the gas particles here. Now, I think this is a nice example to look over, because in this example, we're not just dealing with the collision rate equation, but we're also bringing in the ideal gas law in order to help us see the proportionalities and how the variables relate, and how you're able to bring in the information that the problem is given. So although the problem didn't explicitly tell us the number of moles, you can find that by bringing in the ideal gas law to see that that's the difference between these two samples, and that's what you use in order to find the answer here. That brings us to the end of chapter 5. And so there are a couple of slides at the end of this presentation that contain a list of topics that we discussed that you can see and use as a study guide if you'd like. And with that, we'll finish chapter 5, and up next, we'll start chapter 12, which deals with quantum mechanics.